So as I was kind of saying, is that we'll continue on from yesterday, where we rapid fired through a whole bunch of topic 12, 13, at least rapid fires I feel comfortable with. Still ended up being like 30 minutes worth of our time. But the rest of that time was talking about hypothesis tests, and I went to pretty gory detail, a little bit like what hypothesis tests were, how they're used, considerations you have to do. And then at the end, we kind of saw a t-test, right? And we actually saw, hopefully seeing the actual performing a t-test made you feel pretty comfortable and like, oh, this seems pretty straightforward. Like I don't have to do too many crazy things. And that's actually, I think, the general feel of statistics in general is, at least for a lot of stuff that we do for inferential statistics, it's not that anything in particular is like very difficult to do. It's more like the context of like what we're doing and understanding like, is this valid, or like, how do we interpret this? And that's what I was really trying to emphasize yesterday. So we're going to continue our discussion today on like hypothesis testing, all that good stuff. We're going to talk a little bit about like the factors like significance level, effect, and then we'll go into something called Anova, which is kind of a special, kind of a variation of a t-test that's used for multiple comparisons. And then we should get to the point where we talk about topic 16, which is A/B testing. And A/B testing will be basically an application of hypothesis testing. It's actually not too different, but it sounds much more fancy when people talk about A/B testing. So let me go start sharing my screen and we'll get going. So let me go ahead and put this. Oops, my window's gone everywhere. Okay, I'll just share my screen. I'll have to resize the window once I share. Okay. So I see this little skinny guy. I'm gonna expand this guy out. Cool. You guys see all my my files here for the notebook? Cool. All right, see thumbs up. Awesome. All right, so we are going to focus again on probability statistics, and then we're going to be focusing on experimental design. And so we went through a whole bunch of these little notebooks and stuff yesterday. Excuse me. And so what we're going to do is actually go through basically the rest of them. And so we talked a little bit about hypothesis testing intro, experimental design, all that good stuff. We talked about t-tests. We actually talked about Welch's tests. So, and Welch's tests, if you guys just kind of look at this real quickly, just what we had last time. And you can see basically to actually perform the Welch's tests, Welch's t-tests, we can just basically pass in our two distributions, right? You can think of this being like, you could even have this as like a series, essentially. You could pass this in here and you get your t-statistic, right? And your p-value. Note that to perform a t-test, what we call a student's t-test, where the variances are equal, you would just pass this in from SciPy stat, you see import from SciPy, import stats, stats.t-test ind, right? And you can pass the two distributions there. If you want a Welch's t-test, what's the biggest difference between a Welch's t-test and the classic student's t-test? Do you remember?
It accounts for the sample size for the experimental data as well as the normal one, I guess.
Yeah. The experimental control, right, is the two distributions, like RSV1 here, RSV2. Those are two distributions. It accounts for the number of samples, and then also tied slightly to that is the different variances between these two groups too. So to say we want to perform a Welch's t-test, we would just say, well, let's see if I got to import this guy here. Sorry. That's what happens when you run code later on. We can actually say equal variance equals false. So I believe it's equal variance, or sorry, yeah, it's equal variance. Equal variance equals false. And so that will perform an actual Welch's t-test because it means the variances aren't equal. And if we run this now, we should get a slightly different answer. And still, in this case, the p-value is usually what you'll really care about. And the smaller the p-value, the more likely you'll be able to reject the null hypothesis. Okay, cool. Sound pretty good? That was basically everything summed up, like not summed up, but like the main thing that we'll like use from yesterday. Okay, so then it goes through like, okay, all these different parts. So this is why I say it's all about context, right? It's not just about like performing the actual hypothesis, it's about actually the context. So we're going to talk about a few things like types of errors and warnings, and then eventually multiple comparisons. So I'm just kind of opening these up here. Multiple comparisons. It's alphabetical. I should know how to do that. Okay, so I'm not going to go into full detail of this because you'll see this more when we talk about classification. But there's types of errors that we can make when we actually like do inferential statistics and really classification. There are two types that we will talk about the most, are basically false negatives and false positives. So this little diagram actually comes from Wikipedia here. And basically you can think of like, there are true like positives, like these exist, like they are actually like, if you imagine like, if you're testing for a disease, like you are actually sick with this disease. And then there's a certain segment that people who definitely do not have the disease, right? But when we do a test, and then later on we'll talk about like machine learning models, you can actually say like, okay, like our model or our test captures say, oh, it's identifying these as actually having disease. So you can see here, like these are all, this screen right here are all the people or subjects or whatever that would be positive, let's say for a disease, would be positive. And these guys right here in this kind of semicircle are all the ones that the machine says these have the disease and they actually do. So these are true positives. Now, outside of the circle, basically the model, the test is saying it's not, these points are not positive. Like it would label as negative, saying, oh, it's not, there's no effect. But in truth, it actually does. So we call these false negatives, saying, oh, the machine, or I should say the machine, the model or the test is saying, oh, these are negative, but in fact they aren't negative. So false negatives. And then similar, we have false positives, everything in the circle here, the test is labeling as positive, but some of these ones aren't actually positive. They're actually negative, so we call them false positives. And then we have the true negatives here, which like in this case, like the disease, like, oh, they don't have a disease, and the model or the test actually identifies them saying, oh, they don't have the disease. So that's the 4 different places you can really be in. Now, we'll go into a lot more detail, so I'm not going to go through this whole notebook, but some example, like, we call these things like type 1 errors and type 2 errors are basically representing of like false positives, which these are false positives over here, and false negatives over here. And in a lot of ways, there isn't like a specific way to say, do we care about false positives more, or do we care about false positives or false negatives more? Like, what should we care about? It's all based on context. So an example of like a false positive, like if you heard this from like a doctor, you probably hear like false positive a lot and stuff like this. And this is actually where alpha comes from. Alpha is actually saying how many false positives are we willing to accept. So this is a percentage. So a 0.05 alpha would basically 5% of the time we'd be willing to accept a false positive rate. 5% of the time accepting false, or sorry, if 5% of our results were false positives, like this is good enough. And the way you can kind of interpret this for hypothesis testing is like if we repeated the hypothesis test many, many times, 5% of the time, those hypothesis tests will give us a false positive result. Okay, so basically saying like, oh, there was an effect when there really wasn't an effect. Does that make sense to people? Give me a thumbs up if that makes sense. Okay, I see thumbs up. Okay, so I want you to think like alpha, like your significance level, that, or I should say critical value, but like your alpha is representing the false positive, type 1 errors, okay? False 2, negative, which we'll actually see in a bit when we talk about statistical power, is denoted with beta here. If you guys are familiar with the Greek alphabet, beta. And the way I kind of remember this is that type 1 error is associated with alpha, the first letter in that Greek alphabet. Beta is type 2 errors, the second letter of the Greek alphabet. That's how I remember it. And there's and then in this case, like, what is it, false positives or false negatives? I just remember alpha is always about false positives. So false negatives, we'll see this in statistical power, but basically it's tied to beta. And beta basically saying, oh, if we have a 20%, say, okay, 20% of the time we'll have a false negative. So 20% said we should have rejected the null, but we didn't reject the null. So we get a negative result, but we should have actually rejected it. And this number tends to be a little bit higher, mostly because in a lot of instances, we want more, we want less false positives in a lot of our tests because we want to make sure that like there actually was an effect. Like usually when we're doing hypothesis tests, A/B testing, making a change has some cost to it, whether that's time or money and whatnot. So imagine back to like, let's say a YouTube video. with a little thumbnail, right? And see like if someone clicks on it or not. It might cost money for us to actually like make a new thumbnail and see how well it does. That's a cost, and we want to make sure we don't want to get a false positive, whereas like oh like we think it doesn't have an effect but it doesn't, and we just spent a lot of money to try to actually make that effect happen. Versus like false negatives, like oh we're just going to use the status quo, like we're not going to change anything. And like sometimes like oh we probably should have changed it, but it's probably not going to do a huge amount of harm. Okay, that's why usually this beta tends to be a little bit higher too. Okay, does that make sense to people? Thumbs up if that makes sense. Okay, I see some nods. Cool. All right. So I'll give you a classic example of like this, like in a clinical trial, because like this false positive and false negative won't apply just to hypothesis testing, but also for machine learning models and stuff. And we'll talk about this again. So the classic example is like the pregnancy example is that you have a type 1 error where it's a false positive, where the doctor takes a test and says, oh, you're pregnant, but clearly the person is not pregnant. And then type 2 error being like, oh, you're not pregnant, but clearly they are pregnant. That's kind of like putting a little bit closer to like what you might see in like a clinical setting and stuff. There's a whole bunch of different examples of this disease and justice system, but I won't go into that. Okay, sound pretty good? Okay, so the main thing I want you to take away is that there are two types of errors: false positives, false negatives. Alpha is false positives. Later on, we'll talk about beta is false negative, but main thing is alpha is a false positive. And we usually want to reduce, in most cases, our false positives when we're talking about A/B testing. Okay. Cool. All right. So now that we've got that out of the way, we can talk about some warnings about like hypothesis testing in general. So when we do hypothesis tests, we'll actually see that there's certain situations that can lead us astray from our actual like conclusion. So one common one is multiple comparisons. So I actually showed a little bit of this little comic, right? Where essentially what happens if we start testing multiple things that really don't have any effect. If I have an alpha of 0.05, I'd expect about 5% of the time, right, 1 out of 20 times, that there will be a significant result, a false positive, right? But it's not actually a significant result. So this right here is representing that false positive 1 out of 20 times, or 5% of the time. So like that's kind of like the problem when we do multiple comparisons, where we compare the same thing. Like in this case, we were comparing the color of the jelly bean with causing acne, and it basically is just doing the same test of saying, do jelly beans cause acne, which they found no was like it was no the first time they tested, and they did it over and over and over again because the color doesn't matter in this case, and it ended up being a significant result just by pure chance. So that's kind of the idea of multiple comparisons. Spurious correlation. This is kind of like an interesting term. I don't know if anyone's ever seen this website. Has anyone seen this website before? No, maybe not. It's kind of a fun one. Basically, they find different, like in this case, you can see hanging and suicides and U.S. spending on science, and these correlations that actually match really well. So you can see here is that as the the number of hanging suicides increases, we actually see an increase also in U.S. spending science. So maybe there's a correlation, like maybe there's a causation there. And what this is basically saying is like, no, it's just a pure chance. And it's because basically this site basically looks for all these different possible features, and seeing eventually you'll find something that is somewhat correlated. This one's a fun one, is that films Nicolas Cage appeared in, as the number of films increase, we actually see this number of swimming drownings increase and decrease. Pretty obvious that Nicolas Cage is causing drownings, at least when appearing in films. So again, this is like not true. But the important part is that like your hypothesis test basically will sometimes actually say that this is significant. Like, oh, these relationships are very close together. These are actually significant, when in fact they aren't. So the reason why we have this is mostly because of multiple comparisons. When we compare many, many different things, eventually we're going to find something that is related, or that we think that there's an effect when there really isn't. Okay, does that make sense to people? Cool. All right. So always keep this in the back of your mind especially when you get a positive result, in the sense of that you can reject the null hypothesis. Think about saying, were my methods sound? Like, did I test the right things, or is it possible to do multiple comparisons? And we'll talk about in a second about like how we can address some of those issues. Okay, so that's kind of our first one that we'll lead into. But there's also p-hacking. So I mentioned about p-hacking, and there's a few ways you can do this, but the main thing is I will say is that your p-value, right, it's going to tell you the likelihood of how weird something has to be. But if you're testing many, many times, that can actually be more weird things are likely to show up. If you try things over and over again, something's going to eventually going to happen, right? another thing is that with p-hacking is sometimes adjusting your p-value. So one thing that can happen, I think this is not in here, no, with p-hacking, it's very common, is that you'll get some value that's very close to your p-values. Let's say like 0.051. You're like, ooh, if it was 0.05 or lower, I would have said it's significant. And you can actually see this little on the comic here. Oh crap, redo calculations. And actually, that's actually a really common thing. And this is where you have to be very you have to fight that temptation. It's like, well, I just need to collect a couple more data points, and a couple more data points, and then test if is it actually significant or is it actually not significant. And you do over the hypothesis. That's not a good thing to do, because one is that you're already biasing and saying, hey, if it was significant, you probably would stop. You wouldn't continue to get more data points to see is it really significant. Okay, so you're already biasing, only testing when you get a non-significant result. The second thing turns out is that you can actually do this mathematically and actually show is that if you have a non-significant result, getting a few more data points can actually lead it to a significant result. I think it's about 30% of the time when there's actually a not significant difference. And it's really interesting, but the point is basically if you get your p-value, even if it's super close, you have to redo the whole experiment. You don't just get to add new data points to that to your data, because that can actually influence your influence mathematically if you're going to get a false negative, or sorry, false positive. Okay. Cool. All right. Kind of warning. Unintended consequences. Anyone heard of Goodhart's law? So the classic of Goodhart's law, it's basically saying that when a measure becomes a target, it ceases to be a good measure. So I actually think if you just literally look up Goodhart's law, you'll see a lot of these things. So the classic one I know is the nails. So the idea here is if we're measuring the number, a good measure would be how well are we producing, on these let's say we're a nail factory. It's the number of nails made. Well, then what happens is that there's just many very small nails, because maybe small nails are really easy to make. And that's not really what you want. You just wanted to be able to make more of the same quality nails. And so maybe if you instead measure the weight of the nails, you're oh, how heavy are these overall nails? You might just get a very few giant heavy nails. So the point is basically is that when you start taking a measurement and actually using that as a target, saying, okay, we're measuring this thing, and now we're using this to target of, can we get to this point? That's when you start getting these unintended consequences, and that's what we call about Goodhart's law. For the record, Goodhart, I don't think actually quoted this specifically, and it kind of is modified, but I think you might hear something along the lines especially from economists and stuff like this, where when a measure becomes a good target, it ceases to be a good measure. So one thing you have to be very careful as a scientist is if you are measuring something to see if the results are significant, or some metric that you're using to decide on some decision, right? Or some decision, right? The problem is that if you then take that metric and report that metric and say, oh, we need to increase this, you might have some unintended consequences where the company, whoever you're talking about these things, comes back and try to optimize for that metric, but it's not what you really intended for. So always be aware of that kind of stuff too. Okay, does that make sense to people? Cool. All right, any questions at all about those parts I went over for these mornings? P-hacking, multiple comparisons, unintended consequences, Goodhart's law. No? Pretty good? Okay, all right. So we're going to go back to those multiple comparisons, because this will actually lead us into some more information. Now, this is where there's a few ways we can do this, right? So I'm just going to close this guy so I can kind of go one by one here. So what are the issues with these multiple comparisons? Well, the thing is that because we're testing it over and over again, we're more likely to capture these false positives, right? We reject what we shouldn't, right? The null hypothesis seems wrong, but it actually isn't. And so we actually end up getting what's it called? More false positives, right? It's not really what we want, right? So one thing we can do, I kind of make a little joke here, but we move the goalpost. So the idea here is that if we are doing multiple comparisons, we can actually say, well, let's make it harder for us to actually reject the null hypothesis, because we're more likely to reject it anyway. So hopefully that makes sense. So There's a few ways to do this. One way is the Bonferroni correction. And basically what you do is that you divide alpha. So let's say your alpha was originally 0.05, but you're going to say, okay, let me test the control versus experiment group 1, control versus experiment group 2, control versus experiment group 3, right? If you're doing 3 different comparisons like that, then you would divide alpha by the number of comparisons. So in that case, divide by 3. And so you would need an alpha to be, or a p-value to be smaller than 0.05 divided by 3 in this case. And so what it means is that we're more likely to like not get false positives. But there's a little issue with this. This measurement is really conservative. Like you're almost likely, like essentially you have to find something that's really, really significant in order to find, or sorry, in order to reject the null hypothesis. So it might be useful in cases where like you want to be extra sure, but it might not be ideal for most situations because saying like you end up just getting more false positives essentially. So I was like, oh, that's not super ideal. There's another method that's kind of a combination of this. It's called the Homo Bonferroni method. And there's actually a great, the article on Wikipedia actually does a really good job. And basically it's that p-value must be larger than a modified alpha. And I won't go through the full steps here because it's a little technical, but the main thing basically is that we actually do those multiple comparisons. So it's like, you know, control versus experiment 1, control versus experiment 2, control versus experiment 3, you get 3 different p-values. And then basically you sort those p-values and you basically find like that the p-values after sorting them, where's the last p-value that satisfies this condition? Where in this case, I believe M is just how many comparisons you actually made, and K being the total, K being like the ordering. So don't worry about this. Don't feel like you have to write this down necessarily. But like this is going to be the method. And then you only reject hypothesis smaller than the index K. So the idea here is that if things are really extreme, like you would cut it, like you would say, okay, like really extreme, those are obviously should be, you know, reject the null hypothesis, you know, get a hopefully a true positive, right, result. But the ones that the p-values aren't quite where they're at after multiple comparisons, you say, well, these are small, but they're not small enough, and you reject, you don't reject this, but you fail to reject the null hypothesis, and you know, possibly risk a negative result, but possibly risk a false negative. So the idea there is a little more, it's a little less conservative than the Bonferroni correction that I mentioned. It's a little more complicated. We can do this. And the reason why you do this is that there's a few mathematical reasons, is that it's uniformly more powerful. It's relatively simple. It's not like something you have to like really like, you know, go into deep mathematics. Like this process, even though it looks a little technical, it's not too hard to actually implement. And there's a, for statistics people and stuff like this, there's a closed testing procedure, which actually has some really benefits, some good benefits in there. But I wanted to show you that there's these 2 correction methods. In reality, people say like, well, do I really have to use this? In reality, probably not. But if you're doing more of a scientific and you want to make sure you're very, very careful with your results, you might consider, for example, the Homo Bonferroni method. But also be aware of this. Like I would say that kind of play around with this when you're like starting off. It's harder to actually reject the null hypothesis with either of these 2 corrections. So it's not the most ideal, but it's something that you can consider without having to do anything different. Okay. Now, we will talk about Anova, which is analysis of variance, and we'll look at that, which allows you to do multiple comparisons. But the Anova test is going to be a little bit like we'll talk about in a second. Anova test will tell you, is there a significant result of these multiple comparisons, not which is the most significant result, which is a subtle difference, right? So this is ideal because you can actually say which result is actually significant, but you basically being extra conservative. And the Anova, which we'll see later on, is about saying, is there a significant result in all of these results that we have? Okay, cool. Does that make sense to people, that subtle difference and where this would apply? Cool. Any questions at all? Oh, I see the chat's going on right now. Okay, good. Just comments. Okay.
Hey, Victor, quick question. How many, do you see this very frequently in any of these methods?
Yeah, so this is where I'll say is that in more on the science film, more academia, I'll see more of this whole Bonferroni method. In actual industry, I rarely see anything like this. And I don't know if that says more about the industry versus like actual like use case, but part of the reason why is because you can test this out. You can do an A/B test, which essentially what this will end up being, an A/B test, and like be a little less conservative and then make some changes and then just re-observe saying, hey, did this actually make a change and stuff like that. So I think the idea there is that you have more variables to play with after the fact. So I typically want to do this for like A/B testing and stuff. But if you are in a situation where like we need to be very, very specific, like if you are looking more, like if I'm talking about like a website, like changing the color of their website and like seeing more people click, I would probably less be conservative. But if you're a data scientist working with like developing microchips and stuff like that, and we need to make sure there's a very specific, tolerance that we have, you probably would be a little more conservative because a false negative would actually be less detrimental than a false positive. So does that make sense?
Thank you.
Yeah, no problem. Cool. All right. Cool. So we got over that. We'll see Anova in a little bit, but before we dive really into Anova, what I want to talk about is a couple of things I kind of hinted at was effect size, and then ultimately statistical power. So what's effect size? So I think Chuck was the one who actually mentioned a little bit like effect size and stuff like this, like kind of asking a little bit. And so one thing about effect size is basically just saying, is it significant enough? If the effect is significant, how significant was it? And this is actually really great for meta-analyses because we can use, if anyone's familiar with meta-analysis is basically used to compare multiple studies and stuff like this. So what we can do is that we can actually calculate a threshold of two populations. And you can imagine these are two populations. I have one in pink here and one in blue. And basically we're just trying to calculate like how much is this overlap and how likely is it overlap. So the thing is that this has, for example, a larger effect size because there's a difference between this pink distribution and this blue distribution. It's like from the means of about 4. So you can see there's a bigger effect size. This does have an effect. You can see that there's a slight effect here, but it's very, very small. So this will actually be more difficult to actually capture in a hypothesis test because you can kind of think about it. It's like, oh, in order to capture that small effect, you have to be really, really certain that effect exists, right? Versus if the effect's very large, it's probably really, really easy to actually see that there's a difference between the two. So there's something like, I kind of had this from before, it's probability of superiority. Basically what it is, one way you can do this is you can basically randomly pick a member from each of the two populations and compare them. This can be useful for samples of unequal sizes. And so like, for example, if you have a very small number of people in the pink distribution and a very large number in the blue population, it might be hard to kind of like compare them directly. So one thing you could actually do is just literally randomly pick from the pink, randomly pick from the blue, and compare the difference between the two, and then repeat that over and over again. This is actually really nice if you can just do sampling. And you can probably just figure out directly, say, hey, like, is there a significant difference? And actually testing, do a hypothesis on the difference between those two. Another thing, which is more common that I see is Cohen's, like using some kind of statistic. So Cohen's D is a very classic one that you can directly measure with the variance between each group and actual number of samples. So you don't have to really memorize like this equation and that, but just kind of look at this right here is that basically we come up with this pooled variance right here. And this pooled variance basically is taking into account the variance of the samples and, variance of the two populations and also the number of variations, I should say sample actually, sorry, variance in the sample and the number of members in that sample as well. And so that combined together, we can then get Cohen's D statistic where we can measure that average mu1 and average mu2 from those two different distributions divided by this pooled standard deviation. And this gives us a statistic D. Note that this doesn't have any units. So it does kind of like, what does D mean? D basically, in this case, is really just kind of like a metric to saying, is there a small effect or is there a bigger effect based on the sample that we pulled up? So we can see here a D statistic for 0.2, the general rule of thumb is like it's a relatively small effect. 0.5 is a pretty large effect, and 0.8 is or 0.8 is even larger. 0.5 means like about medium. And like what does that mean exactly? There's no units in this part, so this is basically relative to each other. Okay, but it's nice because then it gets a direct number that you can like use to kind of like determine a little bit, like get a feel for what the actual effect size is. Okay, so what does this actually look like? So kind of showing you a little bit like how we can build this up. I'm going to import these libraries here, and this function here is just going to help us out. It's just basically going to take in a random variable, and then actually going to output a normal distribution for us. So this RV right here basically is just going to allow us to say, okay, we have a mean, we have a standard deviation of this population, the sample, and then what we're going to do here is basically create a PDF of that sample. So what that looks like, I'll just kind of wrap up ahead over here. Or you know what? Okay, I will just kind of go through this part. So this is basically we'll create our PDF. This right here is basically overlap the superiority. Basically, this will calculate that kind of overlap, like how much is overlapping, and basically which one actually has more of an effect. So we don't have to go through the whole details of this guy. And then finally, actually plotting these out. We basically just are using, if I remember this right, yeah, we're actually using this to create that PDF, and then actually checking out like what's O and S in this case, what's the overlap. So this will make more sense when I actually put this in. So what's kind of nice is that I actually made this so I can put in Cohen's D, okay, and actually say with this effect size, what would those distributions look like? So I'm kind of working backwards in this case. Like, it's like, oh, what does a Cohen's D of like 0.2 look like? So what this would look like would be something like this, where we have a very small difference between the two. The superiority, which I kind of described, is like if I randomly picked members from the purple, or not the purple, the pink, and members from the blue, I would sometimes get people who were like a little bit above, a little bit below. Basically, we'd have something around like 45% of them being actually above those values. And you can see the overlap's pretty decent. If I have a Cohen's D closer to like 0.5, which is kind of a medium effect, you can still see there's a significant difference between the two, but definitely bigger than the original difference here. And you can see here is that now we have less likely of our superiority of actually making a mistake, of getting the wrong, like for example, pulling a person from the pink, and then finding out that, pulling a person from the pink, pulling a person from the blue, and then seeing the difference between, it's like, oh, the blue is actually smaller in value, and actually the average is higher. So we only did make that mistake about 36% of the time. And then you can see here, I put like closer to like 1 here. You can see this is a relatively large effect right here. So you can see there's a pretty big difference here. And then you can see if I get really significant, I had 4 here, I think. You can see like the effect's so large that there's almost like no chance for you to like overlap. Like you still can, but it's unlikely to happen. So you can see a little bit of what that looks like. Okay. So I'm just showing this mostly to get you guys a feel for this Cohen's effect. So like the question usually comes like what should I really care about? And it's like the example of this might be is if you have like, let's say, a species of like, I don't know, mouse, right? And you look at like male and female mice of the species, and you say, okay, like what's the significant difference between those weights? Like you can think of like relative difference, and maybe male mice in the species and female mice in these species are actually very, very close. There's a slight tendency towards male mice to be a little bit larger, but like that effect might be so small that's almost insignificant that it doesn't really matter. Versus something, let's say, I don't know if anyone's familiar with elephant seals. Like, you know what I'm talking about when I say an elephant seal, right? Big, massive creature. And this species has a very significant difference between like the males and females. Like the males are much heavier than the females. Okay, so in that case, either Cohen's D would look something like this. Now the thing is, between that mouse and elephant seals, they both have a difference between male and female. In fact, they could have significant difference, like statistically significant differences, meaning that there is an actual difference between the two species. However, the effect between the two might be might be different. And that's the kind of idea where you want to make sure you know how much of an effect that you want to look for. Is that if, for example, that effect to change the website, and like to say the effect is like how many more signups there are, what is the effect that we want to look for? If we don't see an effect that's large enough, then we don't want to look for it, or like it's not worth us changing it. So that's kind of the idea of like why we use Cohen's D, to kind of get an idea of how much that effect, because you can get a positive result, reject the null hypothesis with a hypothesis test, but with a very, very small effect. Okay, does that make sense to people? Cool. Okay, so a quick way to do that is with Cohen's d, and it's just one way to do it. All right, so this will lead us now into statistical power. So kind of jumping a little bit into different parts, but bear with me, it does kind of make sense. So statistical power is one of those things that I think tends not to be talked about. It's like, I don't know what it is, but it's like people don't like really talking about it as much as like alpha and like, p-values and stuff like that, but it is actually really useful. So basically statistical power is basically saying how good is our test against type 2 errors, against false negatives. And so power is defined by 1 minus beta. Hey, recognize beta here. Beta is basically saying how many false negatives we would expect. So you can see power is kind of like 1 minus the number, like the percentage of false negatives. So note that then this number must go between 0 and 1. 1 basically tests perfectly, identifying, it perfectly identifies rejecting the null hypothesis when it's wrong. So like if the null hypothesis is wrong, it rejects it every single time, would be a power of 1. Note that, like I kind of mentioned like last time, alpha, power, and sample size and effect size are all related together. So you can't have a high power and a high alpha with a low standard deviation, or sorry, low sample size and low effect size. You just can't do it. So kind of show you a little bit of this. I like this this interactive web page right here, is that if you imagine there's, in this case, like the null hypothesis and the alternative hypothesis, think of this like the control group in the experiment group. We can, for example, and we can solve for different parts. So let's say I'm going to solve for n, just because that's one that we classically do for A/B testing. So we say, okay, we want a power of 0.8. That's usually pretty typical because we want about 20% of the time we might get a false negative, but we're okay with that. Alpha level significance level for alpha is about 0.5, about 1 out of 20 times we'll get a false positive result. And then effect size, if you notice how I actually adjust this guy right here, you can see is that, let's see if I can reset the zoom a little bit. There we go. So you can see that here's the effect size, and then as it increases d here, you can see the effect can be very small or very large. So the idea here is that we can change, like, okay, like this is not something you get to control. This is usually something like that's either inherent for the population, or you might control in the sense that like, what is a decent amount of, like, what is an effect that we're looking for as a business? So that's where this d comes from. And you can think of it crest to crest, okay? And with that, in this case, all 3 of these things are tied together to our sample size. So it turns out if we want, something that has a very, very small effect from each other, so it's gonna zoom in a lot, so you can imagine those peak going up, we would see we need more, a larger sample size to actually make this significance level of 0.05 and power 0.8. If I have a very, very large effect, right, so let's say closer to like 0.8, we'll see here is that, well, basically I don't need that many people to actually sample because the effect's so large that I will see it almost immediately. Okay, does that make sense to people? Okay, so typically you can solve one for the other essentially. Now, depending on the situation, so in normal hypothesis testing, usually we're solving for D. It's like, what is the effect size, and like, what kind of sample size would we can we have, and what kind of effect size would we expect? But for A/B testing, usually we're actually solving for N. Is that we say, how many people do we need to sample? How much do we actually need to collect to see if there's a significant difference? And that's where you can adjust these things. Note that you can see here, I'm going to use a one-tailed test here just because it's a little bit easier, is that you can see this alpha in red. That is basically like the times we reject the null hypothesis, but it turns out that the null hypothesis shouldn't have been rejected. Okay, and then beta here, or sorry, the power here, or this is beta, is the time that basically when we have, we fail to reject the null hypothesis, but we should have rejected it. And you can see here, that's where the Z critical is basically like where that happens, like what kind of, essentially what kind of value what would fit in here. So if I move, I think I can move this one. No, I can't. You can imagine like if we ended up on this more extreme side over here, we might actually end up rejecting something that we wouldn't have planned to reject, versus the opposite, where it's like, oh, like we failed to reject and we made a mistake in that sense. So this is kind of like what this is representing between these 2 different distributions. But I think the important part in here is basically looking at saying that as we adjust, if we lower our significance level, note that we're less likely to get a false positive. But of course, we can actually see here is that in this case, we're solving for n. So let's like go to its power. If I go from 0.5, I'm keeping n the same, and I lower my significance level, right? We're less likely to make a false positive mistake, but our beta, our statistical power, is going to get weaker because our beta is getting larger and larger. We're more likely to make a false negative result, which hopefully makes sense, right? If you're more careful and not rejecting the null hypothesis, you're more likely to fail to reject the null hypothesis when you really should have rejected it. Does that make sense to people? Yeah. Cool. So the big thing I really want to like emphasize is that like how you can adjust these values to solve for one of these other things. So setting 3 of these values, you can then solve for the 4th one. Okay, does that make sense to people? And for hypothesis testing, typically we have power, alpha, and n already set. We already have the data we have, and we're just basically seeing what was the effect size between the we will only be able to really reject it with alpha, power, and n set with a certain effect size. With a larger effect size, we don't know for sure. But usually it's the opposite, where we're actually designing an experiment for A/B testing, where we actually want to determine what n is and say how many people do we have to add in there for a certain effect size with these certain parameters. Okay. Cool. Yeah. So I'm going to share this on the Zoom chat so you guys can play with it on your own time as well. But yeah, so that's the main thing I want to talk about for statistical power. So a little bit, again, like why this matters for power in particular, because that's the one we're talking about right now, is that this kind of, I hinted, is like adding more samples to P when P is close to being significant can actually lead to us rejecting null hypothesis when we really shouldn't. So I mentioned what you can do. One is you can do a power calculation before the experiment and determine the number of samples needed. So that way you don't change n. Because remember, going back to here, if I increase n now, if I increase n, what's going to happen is that basically I need a larger, a smaller effect. I can detect a smaller effect, which isn't quite what we're looking for. So you can kind of think of the power as the probability of getting a correct answer for your small p-value. So just kind of be aware that can be done. The classic, not the better, but like one thing you can do is actually just like redo the experiment if you do find it like really significant. However, of course, that's always possible. But in a lot of times, like when you're talking with the business, usually you can just redo a test if you already determined what the size is supposed to be ahead of time. There's some other more details of what you can do, but I won't go into details right here. It is in the notebook that you guys can access. But basically, one thing you can do is actually solving for n after the fact and actually using other data to kind of use this to determine effect size ahead of time, so you get a better idea. But this is more in the context of a hypothesis test, more in the science kind of realm, if that makes sense. Usually when we're talking about hypothesis tests as data scientists, we're usually talking about as an A/B test. And usually the effect size is something we can kind of determine that is like, we can say, oh, well, the effect size needs to be this big in order for us to actually make a change, because it's going to cost this much amount of money or this amount of time for us to make this change. Okay. Does that make sense to people? Cool. Yeah. All right. See nods. Cool. All right. Good to move on. Any questions? All right. So I'll move on. Okay, cool. So went through effect size, multiple comparison, all that good stuff. So let's see here. We have about 40 minutes left. So that's good. We're going to talk about Anova real quickly. So this is kind of a solution to some multiple comparisons. Now, it is an acronym, right? So like I said, like analysis of variance. So what does that exactly mean? I think it's kind of, it sounds really confusing, but basically it's actually kind of cool. What you do, you can look at many different segments of like many different populations and see if there's a significant difference between those populations. So kind of like to summarize it without doing any math and stuff like that, is that we're basically calculating a statistic, and this turns out to be the F statistic, or F ratio, means the same thing, to get a p-value. So it's kind of cool. It's like once you know what hypotheses are, you can use whatever statistical tests you want, and it basically translates back to a p-value and a critical value alpha. So basically what's happening is like how much the groups vary. So this is me going a little bit technical, but basically you're comparing a couple things. One is the residuals from the mean. So if you imagine, this is where I get to draw a little bit. Oh, geez. Zoom put my window all the way over to my third screen versus right in front of me. Okay, so if you imagine like I have like a group right here, and imagine more like a box plot kind of group, but I have a group that is, if this is the y-axis right here, okay, so this is the part that can vary. Let's say like the ages of like different groups or whatever. Let's say, let's say of different countries, and like the ages of that country looks like something like this. Let's say this is like the US. Let's say this is like, I don't know, Japan. I'm making this up. I don't know if any of this is actually true. And then we have a final group. I don't know. Antarctica. Why not? Okay.
You can't see anything.
You can't see anything? Oh my goodness. Okay. Well, never mind. I'll tell you what, Zoom is killing me today. Tell you what, I think I have it shown. Yeah. Sorry, everyone. So tell you what, I think I have a little bit later, I can show you a little bit of example groups, and we'll come back to this part. But basically know that you look at two things. One is how much the groups vary from the total. So like saying like each group, how does the group vary from each of the total? So you basically see like the mean of all the groups together and seeing how much does the mean from the total mean vary from that. And then we also have how much do the groups vary from within. So looking at just one group, how much does the individual points vary within the mean of that individual group? Okay, does that make sense? Hopefully you guys can kind of picture that a little bit. Okay, and I'll show you a little bit. Then with that, we can actually calculate the F statistic. We don't have to worry about this number as we kind of see in computers. We can kind of just make the computer do it ourselves, so we don't have to actually remember these parts. But you can basically see is that it's a relationship of saying the difference between this, how much the groups vary and how much the groups vary within. Okay, some quick assumptions is that one is that the samples are independent, that each group is independent from each other, that picking one member of the group does not affect you picking a different member of the group. Okay, so that's kind of, usually you can assume most of those things, even if it's not 100% true. Each sample is from with a normally distributed population. So the idea here is that like our population actually can come from a normal distribution. Turns out you can actually get away with a little bit that's not quite normal too. So it turns out not too bad. And then finally, the population standard deviations of the groups are all equal. This property is known as Homo Scholasticity, which is a mouthful, which we'll see actually again next week when we talk about linear regression. But the idea here is that the variation, the standard deviations of the groups are all about equal. They're not like hugely varied all over the place. If these assumptions are not held and like you feel that there's like, oh, like it's just not, it's not something we can kind of like squint our eyes and say, it's close enough. You can use something called an H test, but it has less power. So it means you're more likely to get false negatives and stuff. Typically, Anova does well enough for most situations. Again, this is going to be more where you get very more into the scientific, like very, very specific and want to be very, very careful. But yeah, just know that basically the same process is the same, just we're using a different kind of test. All right, so kind of give you some basics of that. Let's actually see how you would do this. So there's actually two ways you can use, no, I think you can use stats models, and then I'm going to use SciPy because that's what I'm most familiar with and actually like SciPy a lot. They're basically the Anova is not called Anova in SciPy, it's called F1 way. So basically know that this is actually Anova, but it's called like the F test, which is really what Anova is doing. So I'm just going to import my normal libraries. I pulled up this data. This is actually from the documentation if you check this out. So basically these, if just for the record, I think these are different areas, and these values are different measurements of mollusk shells. So there's like some kind of like oyster or something like that from these different areas. And basically these are the measurements of like how wide their shells are or something like that for context. So there's 5 different groups here from these different areas with these different values. And basically what I'm doing here is I'm making it so we can see a little bit easier in a data frame because we're more used to that data frame. So right here, you can see our values. These are the actual area that the shell was coming from, and then the shell I standardized these values are standardized. So they've already been scaled over and everything like that. And just to kind of show you what that box plot looks like, you can see here, oops. This is the box plot. And you can see this is kind of nice, for example, if you ever do a swarm plot, you can actually plot out the data points on this y-axis. So you can actually see the individual data points. I kind of like this for box plots because then you can directly see not just the box plot, but the individual points. So you can see here, Petersburg, except for 2 really extreme values, are mostly clustered together. And you can see Tillamook, kind of like more spread out and maybe a little bit higher than some of these other areas, or maybe a little bit lower than like this area. So that gives you an idea. And what we want to know is, hey, is there a significant difference between the different areas for in this case, the shell width, or whatever the shell size of these individuals? And this is where we could technically do a hypothesis test to compare Tillamook with Newport, Tillamook with Petersburg, Tillamook with Magadan, and I can't read the last one because my font's even too small. But basically, we could do those multiple comparisons, and then we'd have to compare Newport with these other areas too to see is it significantly different. And you can see already that's a lot. 1, 2, 3, 4, 5 different groups. That's 5 factorial. No, not 5 factorial. But this is another combination, right? So it's like, oh, like that's a lot of different comparisons. So the Anova will tell us basically, is there a significant difference to look for, and then actually look for that difference. Okay, or it's not. Then what we can do, if it is significantly different, then we can actually look for that difference and kind of explore a little bit better. So there's also a different plot we can see here is the violin plot. So have we seen violin plots before? More or less? Okay. I like violin plots because it's kind of like, you can kind of imagine like it's a PDF on its side. So you can actually like it's a PDF on like vertical. So you can kind of imagine like half of the PDF in there. And it kind of helps us just visualize a little bit where this is. So I don't think I can annotate this, but kind of I'm going to walk you guys through what I was talking about with like the difference between the groups. If you imagine the average is somewhere like right here in the total group, like I imagine a straight line with my cursor. You guys see my cursor, right? Okay, good. So you imagine the straight line with my cursor here, and that's the average, right? And then what we'd say, okay, from the average here, you can see these are the different averages. Okay, how much does this average differ from each group? And then summing that together, and that's like, oh, that's the variance of the groups from the main average. And then what we look at, say, okay, let me look at the variance. I can look at the residuals, but like basically how much do the points vary within an individual group? So we say, okay, like, well, this is the average, and like this one spreads out really far, but we saw this one over here. Let's pretend like, oh, like they have some really extreme points, but most points are right here, so the average is really small. Like the variance between that is very, very small. And then we use those factors to actually calculate the F statistic, and then we use that to determine our p-value. Okay, so that's kind of like what we're doing here. So to actually perform this F one way, the Anova, basically all I have to do is just pass in literally just a different different groups. And if I do this now, you can see here, boom, done with the test. I get the F statistic, which again, it's a little bit harder to interpret, but you can report this. The part that we usually typically like care about like interpretation is the p-value. And see the p-value in this case is 0.0028. So you can see p-value is relatively small. In all likelihood, we had an alpha value probably about like 0.05, 0.025, maybe at the smallest. This definitely would be significant. So we say, yes, there is a significant difference somewhere. These are not all the same. That's what the Anova says. It doesn't tell you which group is different from the rest of them, but it says that there is a significant difference amongst these groups. Does that make sense? Okay. So our next steps would be here is probably doing multiple hypothesis tests between groups that we really cared about. So we still wouldn't want just to go straight into a multiple comparison because then we could also get results. We probably would say, okay, we know there's a significant difference. What are the things that we actually care about? Do we care about comparing all of them together, or really it's like, oh, really want to see if Newport and let's say Petersburg really are significantly different from each other? You can test that then and like only do one comparison versus like multiple comparisons finding some kind of change. Okay. Does that make sense to people? Cool. All right. Any questions on like that process? Really, most is, I mean, look at this process. Most of it's me just showing you guys the data. Really, this is like where the magic happens. It's like really one line.
Yeah, quick question about that one line. Stuff like Newport and Petersburg, is that just like lists of numbers? Is that the type that those are? I might have missed that.
Yep,
Okay.
it's a list of numbers.
You're just
So-
doing one way on 5 lists, so or however many lists of numbers, and then okay.
Yeah, and if you look at the documentation, that's what you see this star args. Basically, it's like, oh, that star args means that there could be multiple arguments, and then the last argument is axis equals 0. So if you had something like a NumPy array, you can say a different axis, and you can see in the here the parameters: sample 1, sample 2, array like. Array like just means a list, a NumPy array, a series, something that has something like an ordered. It doesn't have to be ordered like in this case. I think you could use like a set even. But the point, well, maybe set wouldn't make sense because it would be values. But feeding in something that's an array like, and then putting that in, and then you can see returns our statistic and our p-value. Okay. Cool. Good question though. And that's why I always say, like, I try to give you guys the documentation with these very new stuff. You could technically, you guys already know this too, but worth repeating. If I do like Shift tab, you can pull up the documentation here, and it's actually literally the same thing up there. So. I usually like looking at it like this. So cool. All right. So good. We still have 30 minutes, right? Yeah. Okay. So we're good on time. I just want to show you guys also stats models, which the curriculum does use a lot. So I'm just basically showing you how to do stats models. Stats models. Have we seen it before? Stats models. Give me a thumbs up if we've seen this. No. Okay. I see some head shake. I see some nods. If you go in the curriculum, you'll probably see a little bit more. And you'll see it in linear regression. I personally don't use stats models for the record, but plenty of data scientists do. And it's actually flavored around a lot of the R programming language, which is actually why a lot of the things that get outputted will look different. I don't come from R programming language. I come from Python. So this stuff looks a little different for me, but it's actually really useful. Stats models is probably the most mature because it's borrowing from the R programming language, which is very stats heavy. It's a very mature stats package. That actually does a really good job of reporting values and stuff. So you'll see the difference in between these two, but know that they effectively do the same thing. With SciPy and other, like for example, we use sklearn or scikit-learn, they can do the same stuff, but you have to essentially build it up yourself. So you have to kind of like tell the computer, well, I want these things, and then it'll print those out for you. But anyway, I'll show you a different example of this case with about chocolate. So I'm going to import this guy. The main thing we need is SM, which is basically just saying stats models, and then OLS. So ordinary linear. Basically, this will be used for us modeling, which is really what Anova is doing. And then I'm going to read this data in here, and you can see here I got some cool little chocolate beans. So these are basically different chocolate beans. Some attributes. Each data point is a new chocolate bean, and basically tells you like the company, specific, like was it specific bean, reference. I don't know what the reference is. Review, the date, it looks like, with the cocoa percent. So basically how much, like cacao, I guess, cacao, like that. Whoever knows chocolate better. The thing that makes chocolate, like how much percent that's in there, and so on. So we can go through there. So let's go with something really simple. I'm going to just basically just choose some columns. So in this case, I'm going to choose, or we're going to choose like a specific target. So let's say choose target as the rating in at least one feature. So I just want to see a little bit what I've done. Oh, I didn't have this put together. Pass Victor, why do you do this? Make me work harder. So what we want to do is pick a specific column. So let's say, okay, let's say DF, cacao, and our target is going to be the rating. So we want to basically predict saying, is there a significant difference in the rating? So let's say target. Okay, so we have now our target here. Okay. And then we can also pick a column. So I'm realizing I'm a little shorter on time. Would you guys want me to do this part, or should we just go into A/B testing? If we have time, come back to this. Because otherwise I'm going to end up typing a lot. Thumbs up for going to A/B testing, and we'll come back to this if we have time. All right, thumbs down, like, no, I really want to see this stats models right now. Okay, the only thumbs up I saw were for going to A/B testing. So let's do that. If we have time, we'll come back to this. But main thing that you'll do here, it's in the curriculum. You can use OLS to perform that Anova directly. Okay. I don't know why I didn't fill this out ahead of time. Like I think I thought I had more time. So all right, let's go over to A/B testing. So just know that since we did skip over that stuff for stats models. It's the same process. It's just like you just choose your different groups and say, okay, let me feed these different groups into the Anova test. Okay, so A/B testing, and then if we have time, we'll do actually a walk through that. So A/B tests. Who's heard of A/B tests before? Yeah, so this is a pretty common, like I think it's pretty common, like you'll hear it a lot in the industry too, like in tech and stuff. And basically all like A/B tests are like our hypothesis tests. Like it kind of makes me like laugh a little bit because people talk really highly of these A/B tests and like software engineers. It's just a hypothesis. That's really what we're doing. So the classic is like we have a new website and we change out the layout and we just want to see, does it increase the number of sales on that site? It's like, hey, if we change the format, does this actually increase the number of sales? That's kind of a classic example. Like you might want to ask, and if you're a data scientist, they'd ask you, hey, how do we know this? And that's where A/B testing comes in. So here's a quick question: when shouldn't you use it, or at least when do you think you should tread lightly? Haven't got an idea of like when maybe it'd be hard to get results from this. Maybe just think about it to yourself a little bit. But the classic one is basically when you have a new feature to old users, is that by putting a new feature in there, like, I don't know about you all, but like whenever something changes, like imagine your operating system updates or like your phone, changes or whatever, or the app changes, like you might have some initial reactions depending on your relationship with that software, right? So one is the novelty effect, right? Which is like, think of like the classic, like, like especially if you like really like the stuff, you're like, oh my gosh, like this is new thing, like I love it, it's new, it's like awesome. Like think of like really hardcore Apple fans who like, it's like, oh, every time it's new, it's like amazing and awesome, right? Even if it's not necessarily the general consensus. So the reason why you want to be careful about this is that if you introduce a new feature, it might affect the results, and that it's not really that the feature is better, it's just maybe just people's reaction to that feature. So the idea there is like, here's a really like fake scenario, right? It's like a town's been out of soap for 3 weeks, a new shipment comes in. It's like, oh, we sold out shampoo in the first day. Every day will be like this. We need to bring shampoo every single day. It's like, well, clearly that's not true, right? Is that everyone has it now, right? And people's like, oh, I get used to it and everything like that. You can think of the same thing like a feature, right? Another one is kind of the opposite of this, is change of version, right? It's basically like someone's been using this program for so long and then like it's changed on them and they're like, this is awful, this is horrible, this completely breaks my workflow, this is the worst thing ever. And there might be some legitimate reasons for that, but maybe it's just because of the sense that sometimes people just users react not poorly, but like negatively on some new change and stuff like that. So those are things to keep in mind when reaction is. So like, how do we avoid these kind of things? Well, we basically wait for we wait for users to die to replace new users. But like, if you are a new company that has like, let's say you've been around for like, or not a new company, let's say you are a company that's been around for 5 years, right? Or something like that. And you have a very solid base, but you're looking to expand. Maybe you only have like a very small number of users. And the goal for this company now is to expand out to new users. Well, if you start doing your hypothesis test initially with like these like more older users that will eventually be replaced by more newer users and stuff like that, or the majority of them will be new users, or that's kind of your new base, you're going to get results from just this old user. So one thing is that you basically wait for those new users to be replaced by, old users to be replaced by new users, right? That's your base. Other thing you can kind of imagine is like waiting for these older users to get used to it. Is that basically their initial reactions, like, this is awful, this is completely different. And then they get some time and they're like, all right, it's not that bad. That's kind of like the reaction. And you just want to make sure that you get that at that right moment versus collecting information and get a negative or positive result that really isn't reflective of the true feature. And it's really just reflective of a change. So the big thing is about making sure you have the right time, you want to give it enough time to actually start testing this out, or know what kind of those users testing it out, like what their reactions will be more likely. But you always want to keep in mind, like, hey, change in version and novelty effect. Okay, does that make sense to people? Cool. All right. Hopefully this seems like really obvious. You're like, oh, that seems like something I really have to care about. But it is some of the things that come up really like subtly sometimes, and it's useful to really think about those before you get into the middle of. It's when you're carrying out an experiment, it's usually good to think of these effects ahead of time versus finding out your data and then trying to explain it away, because then you're never really sure. All right. So here's a scenario. So imagine we have like, should we use the number of users? Sorry. Wow, Past Victor cannot write sometimes. All right, should we use number of users, click-through rate, CTR, number of unique clicks at least once, number of unique views. Okay, so what we want to do basically, like this scenario, is that we want to see if our users will click on this this change in the format. You know, let's pretend like, you know, we changed the logo to like red. Will they actually click onto our site and actually go into there? So this is the CTR, right? Our click-through rate. I'm pretty sure a lot of people have heard like CTR, click-through rate. That's a pretty common metric. Note that again, we always be careful about what metric we're using, but we're going to use this one. So one strategy we can do is actually like using bootstrapping, bootstrap the sample. So we talked a little bit quickly about sampling, but one of the aspects is bootstrapping, where essentially we sample over that our group. And we can use that then to simulate using the data to create distribution of metrics. And then we can actually simulate using the null hypothesis to create distribution, normal curve, variance from the distributed samples. So I'll tell you is that this is like one strategy you can do that I've seen people use in the past, but that's partly because people didn't have statistical packages quickly available to them. But you can basically just do this. You can essentially, you can, you don't have to do it this way, but basically the idea here is that you bootstrap your sample to create a normal distribution to see where your samples would appear. But usually what we can do is actually do a hypothesis test directly. So another thing we can consider is that if there's multiple comparisons, if we have different groups and stuff like this, like making sure we do the proper test for multiple comparison groups, right? Because we want to make sure we don't get a false positive or a false negative result. And most likely, if we do multiple comparisons, what kind of result should we expect if we do multiple comparisons? A false negative result or a false positive result?
False positive?
False positive, right? We're more likely to get a positive result when we really shouldn't have, because we're just testing it over and over and over again, right? That's the thing that we're most concerned about. Okay. I think I was showing, okay, I'm going back now to Past Victor. I forgot this was still in here, to be quite honest. I think I was going to show a little bit like what you could do to do a bootstrapping sample. But in reality, you can just use a hypothesis test and just kind of know that you might hear people talk about using a bootstrap sample and like seeing, you know, like it's a significantly different. It's basically what's happening. Let's see here if I can kind of pull up the old chat. Is this guy right here. So I'm going to quickly kind of show you guys what this is looking like. Take a second to load. Okay, basically when you're doing a bootstrapping sample that I was explaining, or I didn't really go into, is that you sample across the alternative hypothesis, the two groups, right? This null hypothesis before group, and then the test group, so the control group, the experiment group, you sample across it, and you see basically the majority of the people, do they show up, like basically let's say, for example, this is your click-through rate. This is kind of like your click-through rate, and you sample across the control group, and you see, is their click-through rate lower than the click-through rate on the experiment group? And you basically just sample across each one and then compare those like averages. That's what you do. Now it gets a little more complicated than that because you want to compare each one. So you take you essentially randomly pick someone from the control group, randomly pick someone from the experiment group, compare those two. Is the click-through rate for, you know, control more than experiment? Yes, then you mark that as a yes, right? And you just do that multiple times, and you say basically count how many yeses you have over how many no's you have, and that will basically give you the probability of saying, okay, like how many people were actually significantly different, and that basically becomes your p-value. So essentially, what you're trying to see is like, okay, do you actually find what's that crossover underneath there? It's an old style of doing A/B testing, but honestly, you don't have to do it that way. Hopefully that doesn't confuse you all more. But all right, let's go into like a little bit of actually performing this and the way I think would be classically you would do. So I think I already ran this stuff, so I'm just going to keep it up in case I mess up with something wrong. I think I have an old version, which is what's throwing me off. So, but anyway, so let's say we get our normal stuff. In this case, I'm going to use some random stuff, so I'm just putting up a seed. And I'm just going to create some data. So this is some random data. It looks like, it's not even random. It looks like just 0, 1, 2, 3, 4, 5. So I have about 9,001 different values here. I'm just basically different IDs. And so this is just for me to create some data. This is usually would already be given to you. So just know that I'm creating something here. In this case, I'm creating a variable 1, variable 2, and I'm giving it an ID. So you can see here, I'm pulling up some random distribution. In this case, these are both actual normal distributions with a average of 0, standard deviation of 5, and average of 4, and a standard deviation of 2. So just know they're 2 different normal curves. So think back to these 2 different groups. Okay. So I have the data. It's like, okay, cool. I got this data. What do I do? The first thing is to actually get a sample, right? So in this case, getting a sample of 200, right? So usually at this point, like before I got into this point, I would probably determine what would be my n that I would need to have a significant result. The good news is that, as you probably saw from this guy right here, usually the sample size can be very, very small and be perfectly fine. So even if I get a very small significance value, and even a very decently small effect, you can see my sample size is usually in the hundreds. So typically we can get things like in the thousands. So as long as it's randomly sampled, right? Assuming I'm not getting some bias and stuff like that. So 200 is probably fine. So I'm going to go ahead and basically sample this. And basically what this is basically creating my samples df. So kind of showing you a little bit. I should probably actually, I go run this again. I'll risk it. Oops. So I'm creating some data. And just to show you guys samples df. You can see here, basically, it's just the different IDs from here, right? So I'm just sampling across this whole data frame. In this case, I think there's a total of 9,000 people, right? So I'm basically saying, okay, and this is their ID, this is their variance, and then basically pulling that over. And then you can see here, I can quickly get some values. For example, I can see the average of their variance, average of, oh, it's not variance, average of the variable 1, average of the variable 2. So you can see here the average here for variable 1. Do you guys remember what the original average was when I created the data? It was set to 0. And then this one was set to 4. So, and my standard deviation in this case is 5.2. This is 2.05, which is really close to the 5 and 2 I set up originally in the data set. Okay, so that's actually pretty decent. But no, normally you wouldn't have that information, but you can see that it follows pretty well. That's because I have like 200 people. All right, so then what I can do is say, okay, I can go ahead and assign these different groups to whether they are a control group or whether they're part of the experiment group. Okay, and so I'm actually going to just do df like this. You can see basically it's just a 0 or 1 to say, are you in control group or are you in the experiment group? Note that I could, if I want to do multiple comparisons, I could have had multiple controls and like different groups and stuff like this. Note that because I'm kind of creating these groups right here after the fact, like you can kind of think of variable 1, variable 2 don't exist yet. And then I assign is control and then see, if you imagine like if you are in control, you basically see the normal website. And then if you're in the experiment group, not in the control, you would get exposed to a different format of the website. And then these variables 1, variable 2s would be the resultant of them, after being assigned the group and being exposed to different parts. Does that make sense to people? So yeah, I just want to make that clear. Is that normally, because this is fake data, this would normally be the things like, oh, I'd already assigned control in experiment and then actually see the results. Okay, you normally won't just assign them after the fact. Okay, all right, so now I have my data. It's like, okay, cool. At this point, like this is where like the real data scientist comes in and says, here's your data. Like, tell me, is there like, should we change the website or not? So what we can do is say, hey, we check for the groups. Are they similar in regards to the random variable? So we can see here is that like, hey, let's go ahead and just plot out, in this case, the variable 1 and then variable 2 and see, is there a significant difference between the control group versus the experiment group, right? Now, we already know the data. So kind of quickly going through, should we see a difference in between variable 1, the control versus the non-control? I see a shake from Safe. Safe, can you tell me why you shake your head?
Well, because they're both random, so.
Yeah, yeah. I just randomly assigned it, and there was no real effect, right? There was no real reason why variable 1 versus variable 0. So we know that they shouldn't be very different from each other. But you can see here, let's pretend like we don't know that information. We plot out variable 1 for the control group and variable 1 for the experiment group. And you might look at this like, oh, like maybe there's an effect there. Like it looks relatively close, right? Can we see that, right? It's like looks relatively close, like maybe there's an effect there. Maybe like, could be interesting, right? Same thing for variable 2. You can see, oh, look, like maybe there's a little bit of an effect here, right? So we don't want to look and explore that deeper. Note that if we actually look at, let's see, variable 1, variable 2, you might see is there's a difference between those two. I just wanted to show like what that variance, what that looks like for like one sample. And you can see here, it's like, oh, for the whole sample, that's what we'd expect, because that's kind of like similar to the overall data. But this is not like we really care about, but you can see like, okay, like this is just from the control and the experiment group together. This is just all the data together just to see if there's a difference between these two. So we're going to do a hypothesis test, I believe, on the control versus experiment group. So basically, I'm just going to use SciPy stats here. And basically, is it significant? Essentially, I'm basically rating a function that's going to wrap around my Welch's t-tests. So I have group 1, right, which will be like control, and then group 2, which will be like experiment. Oh, I actually think, sorry, I'm reading my own working ahead. Okay, I think I might test something else. But anyway, this basically takes our two different groups and say, is it significantly different from each other? Note that I set my alpha to 0.05, but we could change our alpha to whatever we want for whatever we call for. And basically this will get our t-value, our p-value, and basically it'll tell us true or false, meaning that is p less than alpha. If this is true, then that means we reject the null hypothesis and say, oh, the alternative hypothesis is the likely explanation. And then I'll return the p-value just because it's nice to see what the p-value actually was. And then we'll actually look at another situation, experiment versus control. In this case, I think what I'm doing here, I want to make sure I'm reading this right. Yes. So this guy is wrapping around this function here. It's basically just taking the data frame and then saying what variable we care about, and then just looking at is the control and is the experiment group and is the control group, are these significantly different from each other? Oh, I have these switched, don't I? No, these are right. Okay. Yeah, experiment and control. So I basically want to see, is this a control group different from this experiment group in consideration of this variable? Okay. And then basically I'm just testing this is significant, and I can pass in the alpha. And then I have a function now. And now I have two functions and really just one function right here that I can just pass in any group now. Say not even the group, just a data frame. And assuming that is control is one of the features in there, label it 0 and 1, and can just say, hey, you know, is variable 2, is there a significant difference? And you can probably see, oops, let's actually run this guy. You can see is that, yeah, there's a significant difference. Because why isn't there a significant difference? Because we randomly assigned it, right? And you can see here is that I was trying to break this down, like, okay, what would this look like for, pretend like we had var1 and var2 were like experiment and control groups. Like, are these significantly different from each other? If I run this guy, you would see, yes, it is significantly different from each other. That this blue is significantly different from this orange. Okay, so you can see, like, you can write these quick functions here, and basically you just create A/B testing. It's not that hard. And basically just saying, like, determine, like, now, okay, we can say, is it significantly different from the two different groups? If we wanted to change this with multiple comparisons, we might want to actually consider how we want to proceed on that. We might have to be a little more careful. We might, for example, have, is it significant, and actually have it test like an Anova test, right? F1 way. Test the Anova, see is there a significant difference between the multiple groups, and then determine, we could technically compare every single one. Back in the stats days, before computers, right? Like, we had to do everything by hand. One of the arguments for using an F1 way is to basically, the Anova test, right? Is because you want to not take so much time to, like, calculate every single comparison, but you can probably imagine really quickly in your head how you'd write the code in a for loop, right? And be like, oh, just calculate every possible combination. But the other reason why you don't want to do that too is because you don't want multiple comparisons. So usually you might do an F1 way test just to see if it's significant enough, and then take the time to really explore saying, what things do we care about comparing, stuff like that. Because you can imagine if you have 5 different groups and do every single comparison of those 5 different groups, you know, you have a certain number of, like, you know, comparisons, and then that number gets exponentially bigger. I think it actually gets, yeah, close to exponentially bigger. So if you have like 10 groups now, it's much larger, and, you know, you're looking for a needle in a haystack, but then there's a bunch of things that look like needles that aren't needles. Okay, does that make sense? Cool. All right, any questions? Like, again, this is where I think, like, these past couple days, hopefully this feels very like, this is like the easy stuff. Like, this is like relatively easy to implement. The hard part is really the interpretation and making sure that you understand and where these data are coming from, making sure the situations where you don't get the result that you're not expecting, or you don't get results that are biased in any way. Okay. Cool. Does that sound good? Thumbs up, sound good? Any questions at all? How are you feeling about this? Feeling pretty good? Like, yeah, I feel like I can do this somewhat. Yeah. Okay. All right. So yeah, biggest thing here is just realizing that we can essentially do hypothesis tests. Really is A/B testing. The biggest thing that I didn't directly show, which maybe now I'm thinking back, I probably should, is actually determining, you know, how many people to get in your sample size. Like how many people did we actually test on? But even then, like as you probably saw, usually you can get like a good portion, like a decent website, you could probably do an experiment on 1,000 different people on your sample, and that would be a drop in the bucket and be completely fine, statistically significant. The biggest issue is making sure you sample where it is actually random and not going too far a certain group on like of users and stuff. So being careful with that. Like you wouldn't want to, let's say like just like, oh, I'm gonna randomly sample. I'm too lazy to randomly sample. I'm just gonna get everyone who's like in, I don't know, Texas or something like that. It's like, oh, I'm gonna get everyone in Texas and then get everyone who's in like in Missouri and then everyone who's like in Florida and everyone who's like in New York, and like compare those groups. But you didn't care about those groups specifically. You want to be careful with that, obviously, because like, oh, that might have different effects. Okay, cool. All right, well, I'll stop the recording here unless there's any questions you guys want to ask right now. No? Okay.